The main learning outcomes of this lecture still relate to flow structure interactions, and in this lecture we will focus on drag coefficient, how you can estimate drag coefficient, and how you can calculate drag force. So why engineers are so interested in drag coefficients? When you do design, for example, you design a tidal current turbine, you need to know drag coefficient because structures with smaller drag coefficients are more efficient. If you knew drag force, you can calculate drag coefficient, but quite often you actually need drag coefficient to calculate the drag force. The drag coefficient can be used as a relative measure of hydraulic performance of a man-made structure, and can also be used as a measure of the efficiency of the surface or a body to absorb momentum. So how can engineer determine the drag coefficient? There are different methods. First of all, you can use measurements of the drag force. For example, you can measure drag force on a structure and then using the equation which I showed on the previous slide, you can calculate drag coefficient. It could be experimental studies in the lab or studies in the laboratory wind tunnel or oscillatory tunnel. Or there are also other means using various diagrams and to take the value of CD drag coefficients from a diagram. One of the most commonly used methods engineers adopt to determine drag coefficient is to obtain its value from a diagram. And on this slide, I show example of such a diagram for two-dimensional body. In our example, it's a cylinder. The diagram shows the relationship between drag coefficient and Reynolds number. For the cylinder, Reynolds number is defined as approach velocity multiplied by diameter divided by kinematic viscosity. On this diagram, we have two lines, and I will focus on a line that is applicable to the cylinder. The second line is applicable for the sphere, but I will not focus on this in this lecture. When you determine drag coefficient, you can calculate the drag force just using the formula which I showed on previous slides. And for the cylinder, the reference area is taken as the frontal projected area, or the product of the diameter multiplied by the cylinder length or cylinder height. So let's see how the CD is changing with increase in Reynolds number. On this diagram, we have 5 distinct regions. Starting with region number 1, when Reynolds number is small, and for this region we have reasonably high values of drag coefficient, we can observe that when the flow is approaching the cylinder, the streamline follow the shape of the cylinder, and then the streamlines join behind the cylinder. So along the cylinder there is development of the laminar boundary layer, and Reynolds number is small, therefore viscous forces are dominant, and therefore the main contribution to the total drag force is from friction skin drag, and contribution from the pressure drag is negligible. Then with further increase in Reynolds number, we have development of flow separation. So we have 2 flow separation points, and then the flow is no longer attached to the solid boundary, and we have development of the wake region. Therefore, within this wake region, we have reduced pressure compared to the pressure upstream of the cylinder, and because of this, we have contribution of the pressure drag to the total drag force. And in this case, contribution of the viscous drag is reduced, and therefore we have a reduction in drag coefficient. Then with further increase in Reynolds number, what happens? The separation points move further upstream, and this leads to widening of the wake region behind. And because the area where the pressure difference exists in front and behind is much bigger, it leads to increase in drag coefficient. Then with further increase in Reynolds number, the wake region area does not change significantly, therefore the drag coefficient remains approximately constant. However, what happens here? We observe transition from the boundary layer development is transition to the turbulent boundary layer development. But this happens further downstream compared to separation points, flow separation points. Then with further increase in Reynolds number, what happens? The development or transition to the turbulent boundary layer moves further upstream, and it's upstream compared to the development of flow separation points, and this leads to reduced wake region, and because wake region is reduced, this leads to reduction in pressure drag, and this is called drag crisis. And this happens because when we have development of the turbulent layer, for turbulent layer, velocity close to the solid boundary is much greater compared to laminar area, laminar flow, and because of this, the separation points are pushed further downstream of the body, and this leads to much narrow wake region or reduced drag coefficient, and this is called drag crisis. Experiment I will show you on another slide how flow visualization confirms this pattern. So we have region number 1, so flow visualization, and you can see that this confirms the development schematics shown. So let's have a look how you would estimate the drag coefficient using this diagram. So on this diagram you have different lines. You have smooth sphere, smooth circular cylinder, rough cylinder. You also have streamlined sphere and streamlined cylinder. So depending on the problem, you will use the line which is applicable to your problem. So after that, you will identify or calculate your Reynolds number. Assume I calculated my Reynolds number to be 1.2 multiplied by 10 to the power 6. And then now I will need to obtain my Reynolds CD coefficient from a diagram. Looking at this diagram, you can see this is 10, this is 100, 1000, 10,000, and so on. So you can see here 10 in power 6. Therefore, 1.2 multiplied by 10 to the power 6 would be just a little bit on the right hand side from this 10 power in power 6. So I draw an approximate vertical line, and as soon as this line crosses the line which is applicable to my problem, assume I'm dealing with the problem for smooth circular cylinder, which could be like a cylinder of your tidal current turbine, then when your vertical line where you show your Reynolds number crosses the line you need to obtain your CD for, then you draw another horizontal line and read the value of CD from one y-axis. And I read my CD value approximately as 0.42 my CD value. For a tidal current turbine, drag force is dominant and the lift force is negligible. However, at the scale of an individual blade, the lift force is important because it is the lift force that drives rotation of the turbine. Designing a tidal current turbine, engineers also need to use diagrams to determine lift coefficient. For example, it's important to know what design they should use to improve efficiency of the tidal current turbine. For example, arching a flat plate will cause it to induce higher lift forces for a given angle of attack. But the so-called aerofoil sections are even more effective and produce higher lift forces. On this diagram, I show you just a schematic of a blade, which is arched aerofoil flat plate, and some parameters which are shown on this diagram you are familiar with from wind energy module, and this is chord, leading edge, angle of attack, a relative velocity, leading edge radius, trailing edge, and so on. You probably saw this schematic, but I just use this to remind you. So how do the engineers determine lift coefficient? Let's have a look on one of such diagrams. Often diagrams that shows both lift and drag coefficients are used. For example, on this slide I show a diagram that shows both lift and drag coefficients for a specific type of blade, and in this example it's Clark Y aerofoil section type of blade. So these diagrams are produced using experimental data, and diagrams show the relationship between drag coefficient and lift coefficient, how these both change with angle of attack. Angle of attack is the angle between a reference line on a body, and often a chord line is used, and the relative fluid flow, like shown on this diagram. So this is flow direction, and this is relative reference line on a body, and the angle between these two lines is the angle of attack. Looking on these diagrams, we can see that lift coefficients varies almost linearly, approximately linear relationship, when angle of attack changes from around -8 to around 16, 18, the lift coefficient reaches maximum, and then with further increase in angle of attack, lift coefficient decreases. Diagram also indicates that there is like a parabolic relationship between the drag coefficient and the lift coefficient. So drag coefficient is proportional to the lift coefficient and power 2. Therefore, we can say, because there is linear relationship between lift coefficient and angle of attack, so lift coefficient is proportional to angle of attack, we can say that the drag coefficient is proportional to the angle of attack in power 2. And CD increases quadratically with angle of attack. So the greater your angle of attack, the greater CD will be. Designing tidal current turbine structures, engineer aims to improve efficiency of the structure. There are different means how efficiency can be improved, and quite often engineers use measures that are so-called boundary layer control measures. So what does it mean, boundary layer control? It's when engineer either attempts to change the overall flow field to reduce pressure drag and or to increase lift force, or engineer attempts to directly reduce friction drag by means of manipulating the boundary layer flow through the following measures. For example, preventing reducing flow separation by motion of the wall, accelerating the retarded boundary layer flow, or maintaining laminar flow by aerofoil shaping, or reducing the wall shear stress in turbulent boundary layers by streamwise grooved surfaces, it's called triplets, or active control. For example, quite often they use micro electromechanical systems or different polymer additions. Let's have a look how this can be done by changing the surface of the body. One of the good examples how boundary layer control measures are used is design of a golf ball. Let's consider drag on a golf ball. I'm not sure if you know why surface of a golf ball is roughened. If not, I will explain you. Let's assume you have a golf ball with smooth surface. When flow is coming towards the ball, there is development of laminar boundary layer. And because surface is smooth, we have eventually development of flow separation pattern. So we have two flow separation points on both sides of the ball, and there is development of the wake region behind the ball. And this is quite wide or thick wake region. If you recall how the diagram of relationship between drag coefficient and Reynolds number looks like, this pattern will apply to this case when the surface of the golf ball is smooth. So we have flow is coming towards the ball, then we have development of the boundary layer on the surface, then we have two separation points, flow separation points, development of flow separation behind the ball, and there is pressure difference behind and in front of the ball, so a quite thick wake region. Further downstream we have development of the turbulent boundary layer, but because the wake region is thick, we have quite a considerable pressure drag. And if we show this schematically, this is how it will look like. We have zone of high pressure in front of the ball, then we have separation points, and then we have wake region or region over low pressure. And because this wake region is quite thick, we have quite a high contribution to the total drag from pressure drag. So why do you think a golf ball surface is roughened? This is the golf ball when we have roughened surface. So what happened when the flow is coming towards the golf ball and surface is roughened? What happens? We have development of the boundary layer. Then after a short distance, we have transition from laminar boundary layer to the development of the turbulent boundary layer. And because velocities here are quite high, and then these velocities is pushing further downstream development of the flow separation region. So we have two flow separation points on both sides of the ball and wake development region behind the ball, but this is much thinner compared to the case when the surface is smooth. And if you recall how this looks on a diagram, where we show relationship between drag coefficient and Reynolds number, this would look like shown on this schematic. So we have laminar boundary layer, then transition zone, and then development of a turbulent boundary layer. And this development of turbulent boundary layer pushes further downstream development of the flow separation zone. And the wake region or the wake of low pressure region is much thinner compared to previous example, and we have much smaller pressure drag. Therefore, golf ball is roughened and turbulent boundary layer develops before separation, and separation is delayed by turbulence in the boundary layer. And because separation is delayed, the wake region is thinner, and therefore total pressure drag is smaller compared to example where we have smooth surface. On the final slide, I would like to show you development of the boundary layer on the bottom of the ship. So we first have laminar boundary layer, then we have development transition region, and then we have turbulent boundary layer. So this is unique video which shows boundary layer development. So we finished this topic, and now I will create two more videos where I will show you practical examples how to calculate drag force on a structure, on a tidal current turbine, and also how to calculate bending moment on a structure.